you very much, Lan. So firstly, thanks to the local organisers for putting all of this together. I think these days I've become a bit of a user of von Neumann algebras, so I'm really grateful to the global organisers for inviting me back and kind of meet the fix. In particular, it really is somebody who's thinking a lot about how to use von Neumann methods in C3 algebras. It's really great to see all the exciting progress we've seen. So the overarching question I'd like to introduce this talk with. I should introduce my co-authors because I've gone the other way from Corey and written too small so that they can't be read at the back. So this is all joint work with Jose Carrion, Castillejos, Sam Evington, Jamie Gabe, Schafhauser and Tikuisis. So there's a lot of us. So the sort of question I would like to start out with is, if you're going to apply sort of von Neumann algebraic methods to C3 algebras, which von Neumann algebra should we associate? To a C3 algebra. Okay. And of course, there's no right answer to that question. It depends on what you would like to do. So you could, for example, try the bidual. That's really big, but which comes with significant downsides. But of course, it comes also with significant upsides. I can apply the Handbag Theorem. So a really powerful tool is to prove properties of the bidual and pull them back down by Handbag. So, for example, if A is nuclear, then through Con's theorem, we can see that the bidual is hyperfinite. And then we can pull those approximations back down to A through the convex structure and get new complete approximations for A that have better properties than the ones we started with. That's a valid thing to do using the bidual and through powerful methods. And that little sketch argument sits behind this talk, but I'm not going to subject you to the details that appeared in that sentence. I'm mainly going to be interested in the situation where A has got lots of traces, so maybe it has a unique trace, maybe it has many traces, but certainly positive elements can be seen through the traces. So I'm going to be interested in the situation where, let's put it down here, where A has sufficiently many traces. Let's say enough faithful traces, so that will be sort of a standing assumption. Meaning that given any positive non-zero element x, there's some trace which doesn't kill x. So in that case, maybe if I'm assuming that there's lots of traces around, maybe the von Neumann algebra I want to work with is some form of GNS representation associated to that trace. And that would be a particularly natural thing to do if Tor, I'm going to write T of A, the set of traces, is a unique trace on A, or the unique trace on A. And of course, the idea of going to and from the GNS representation goes right back really to the study, at the beginning of the study of C3 algebras. But over the last 10 years, work in particularly the structure and the classification of C3 algebras in the unique trace case has really been driven by this interplay. Standout sort of results go back to Mattui and Sato around 2011, and in particular, Chris Schafhauser and Angel's paper from 2018 is really driven by the interplay at a deep level between A and A Tor when A has a unique trace. But this would also work fine if Tor is 1 over n times the sum from I is 1 to n of Tor I, where the extremal traces, so the trace space, so the unital C3 algebra is going to be closed and convex, so it's going to have extreme points, and suppose there's finitely many of them, say Tor 1 up to Tor n, then working with pi Tor of A, double commutative is a very natural thing to do here. And in both cases, actually, all you've done is you've taken the finite part of the bidual in those two cases. So maybe the right von Neumann algebra for studying this sort of situation, when A has enough faithful traces, is the finite part of the bidual. But then we run into the sort of problem that was articulated beautifully in Stefan's talk, the difference between pointwise and uniform convergence, and that pointwise convergence on a finite set of elements is uniform convergence, but not elsewhere. So if you look at the sort of the deep work that was done relating A and pi to a double commutant, what really matters is that given any element in here, say in the unit ball, I can use the Clancy's density theorem to approximate in A in, say, the 2 norm. And as I go down here, what I'd like to do is to be able to approximate it in 2 norm uniformly in all traces at the same time. And of course, I can do that in this situation because there's only finitely many extremal traces, and uniform convergence and pointwise convergence are the same. But in general, I mean, I'm going to be interested very much in the map from A to A thin, which is going to be an inclusion in the situation when A has enough faithful traces. I will not be able to approximate things here by things in here uniformly in traces.
Excuse me, can you please tell me what A thin is?
The finite part of the bidual.
But what do you mean by that?
The bidual is a von Neumann algebra, it has a type decomposition, and I take it to finite part. Okay, so the solution is to be more general than von Neumann algebras. So I want to consider a larger class of operator algebras sitting somewhere between finite von Neumann algebras and C-star algebras. So of course, what we have is that finite von Neumann algebras, let me call them finite W-star algebras, they're all examples of C-star algebras with enough faithful traces, so let's call those Tracial C-star algebras. If we were restricting, say, to the class of the situation where quasi-traces are traces, maybe we're looking at stably finite units or C-star algebras here. But finite von Neumann algebras are tracial C-star algebras as in C-star algebras with a trace. And what I want to do is put something in the middle, which is this class, which I'll call of tracially complete C-star algebras. This is going to be a new class of operator algebras, such that every finite von Neumann algebra is a tracially complete C-star algebra, every tracially complete C-star algebra is a C-star algebra. And then, instead of trying to do an interplay directly from here to here, I'm going to try and run the interplay through this intermediate class. This really has been going on implicitly for the last 13 years or so, but only, I think, relatively recently started to become explicit. So, for example, I will give you shortly a definition of the tracial completion of a C-star algebra. That goes back to Zauer in 2013. What this talk is doing is telling you what the abstract class that Zauer's construction belongs to. Okay, so that's the overview of what I am going to do. I'm now going to give some definitions, and I'm going to come back and try and tell you why I want to do this later. But I think it will be more useful to have the definitions in front of us. Okay. So before we define one of these tracially complete C-star algebras, suppose I give you a C-star algebra and I give you a trace on A, and I want to know when is the pair A Tor already a tracial von Neumann algebra. What does it mean for A Tor to be a tracial von Neumann algebra? It means that the GNS representation from A to pi Tor of A double commutant, I would like that to be an isomorphism. That would be, so let's call this a fact. Is an isomorphism. Well, if and only if pi Tor is injective and surjective in that setting, which is if and only if Tor is faithful, that will give me injectivity, and the surjectivity I can get from the following condition: the unit ball of A is complete in the two-tone. Right, this is a standard von Neumann fact that the unit ball of a 2-1 factor is two-norm complete, and therefore the unit ball of the finite von Neumann algebra is two-norm complete. So if and only this completeness condition will characterize abstractly when we have a finite von Neumann algebra already. Okay, so that's how we're going to use this idea to define this concept of a tracial completion. So now comes the definition. The pair curly M X is a tracially complete C-star algebra. It's actually quite convenient because it's the first time I've spoken on this at a von Neumann focused meeting. When I speak at this as a C-star algebra focused meeting, we've sort of been forced to converge on this piece of terminology. But it's quite a mouthful and fills up a bit too much of my blackboard. So for the purpose of this talk, I'm just going to call it a T-star algebra. And I was never able to get this through George, but he's not here. So in the papers, of course, it will be a tracially complete C-star algebra. But I actually quite like T-star algebra because these things really are somewhere between C-star algebras and W-star algebras, and I think that they are closer to von Neumann algebras. It's my current way of thinking about these things. So the pair NX is a tracially complete C-star algebra when a few things. So firstly, what's X? Well, X is some distinguished set of traces on M, all traces on M, and I may as well take X to be weak star closed, so closed weak star is the only centre of topology, and convex. Okay, so if I do that, so that's what the X is, and then what I want is that the quantity, let's say X to X, which is defined to be now the supremum over tor in X of tor X star X to the half, so the supremum over all of these trace norms. I would like this to be a norm, so that is a norm on M. So that in particular says that the specified set X is a faithful set of traces, right? You can see any positive element using those traces, so that's the faithfulness condition found here. And then thirdly, of course, and perhaps no surprise, what I want is that the ball of M is 2x complete. So that's a T-star algebra. It comes with this specified set of traces, which I think of as the official normal traces on my tracially complete C-star algebra, because they're all ones that are 2x continuous, and I've specified the other norm. I've defined the objects in this category. The morphisms in this category are the star homomorphisms that preserve the specified set of traces. So phi, beta, say, mx, and y, the star homomorphism, it'll have to be unital because it's going to preserve some traces, and traces for me are states, such that trace composed beta is a allowed trace in X for all allowed traces. Y, these are the allowed morphisms in this category. Cool, so that's a definition, so we should have some examples. So e.g. M tor is T star whenever M tor is a tracial von Neumann algebra, right? That's the content of this fact. That a tracial von Neumann algebra is by definition a finite von Neumann algebra with a specified normal trace. So when I specify that as a trace, it will satisfy these definitions. Okay, so that's one example. The next example is Azawa's construction of a completion. So if I give you a C-star algebra A, how do you get a tracially complete C-star algebra? Well, you complete the unit ball of A. So given A, the C-star algebra, and X inside T of A, closed and convex, we should set A to the X, and we just define this to be L infinity sequences, Xn in L infinity of A, and I would like those sequences to be Cauchy in this norm and then quotient out by the null sequences. So Xn is 2x Cauchy modulo those sequences. Limit Xn 2x equals 0, and then of course you have a canonical map. Let's call it iota x from A into this closure, which will be injective if and only if X is a faithful set of traces. So this is whether or not, of course, whether or not A is a faithful set of traces, AX is going to be a tracially complete C-star algebra because I quotiented out the ones that were not a faithful set of traces. So what you get is that AX is T star, but there's of course an annoying abuse of terminology here, so sort of warning, you know, I'm imagining now that the X here was originally a subset of the traces of A, and of course it's been identified now with a subset of the traces on A, T of X, by just extending them, so there's some nasty abuse of notation. This leads me to my first question, which is a special case of a question I really would like to highlight later on. So I performed the tracial completion, and of course the tracial completion I really want is to consider all of the traces. So the fundamental example is tracial completion A to the T of A with T of A, and this is the object that Azawa was considering, although not in this language. But normally, when you complete something and you complete again, you've stabilized. We can't prove that. So problem one, which I won't write down, so I'm going to write down a more precise version, show that in this example here, there are no more traces. How do I know that when I did this process, some other trace didn't spring up? I really hope that there are no weird traces on my tracial completion, and we have thought about this, we can't do it. I really hope that what's going to happen is that it's going to be like the difference between B-star algebras and C-star algebras back in the day, that some kind of person will come along, there'll be a cute 5-line trick, and that'll be it, and it'll be all homework exercises in the future. But there was a long gap between, if you look at the history, while B-star algebras and C-star algebras were sorted out. So,
what are the abelian C-star algebras?
The abelian, so if you complete, you take an abelian C-star algebra, the 2TA norm is just the operator norm because of that point evaluations give traces. So for abelian C-star algebras, the tracial completion is just the abelian C-star algebra again. And this is the cool thing about this construction, right? On the abelian side, or when there's finite dimensional stuff around, what you're doing is nothing. You're doing topology, you stay with the C-star algebra construction, and then as you move into the more non-commutative situations, this tracial completion brings you aspects of von Neumann algebra. So this 2x norm is somewhere between a 2 norm and a uniform norm, depending on how much abelian structure you have. around.
If you equip M with a finite number of traces and it is a two-star algebra, was it already a Neumann algebra?
Yeah, if X is a finite, well, if you take a finite showcase index, then yes, that's going to be true.
Can you state the problem again? So you want to say?
No, I'm going to state a more general problem.
So but all the traces which are continuous with respect to the two norm are the same as the original.
Yes. Yeah, which is why can I ask no more questions on that until I state the more general problem in 5 minutes?
is that all right? Thank you. These are good questions, but yeah.
I want to make another definition now, so let's go with this here. So we should work out what the fundamental building blocks of these things are. We have simple C-star algebras, we have von Neumann factors, so definition. I'm in two minds about the terminology. We've probably got another few months before we publish, so better names are welcome. Is factorial if and only if, let's see, either X subset T of n is a face. So that means if you take a point in your closed convex set and you write it as a convex combination of two things in T of n, those two things are already in X. Or, this is a theorem of course, factorial of n, where the commutant is a factor for all traits that are extreme in X. You can only expect extreme points, of course, to give you factors, and when all of them do. So we've alternated between tracial and facial, and we're currently on tracial. We've alternated between facial and factorial, and we're currently on factorial. Maybe there's an argument for facial. So that is something I welcome feedback after the talk is finished. So there are various constructions you can do. I'm not going to be able to explain in this talk why this is the right building block, but many of the theorems we can prove, we can only prove under this assumption at the moment that we don't have a sort of version of the measurable decomposition. So somehow, if the designated set of traces then kind of split up and you had some direct interval decomposition here, maybe all of this machinery can be made to work, but this paper is already 120 pages long, and we should probably stick to this assumption.
Just to avoid that I get confused, an abelian C-star algebra will be factorial.
Yes, abelian C-star algebra will be factorial. This is why I think we might end up with facial. There's an even worse one. Every finite von Neumann algebra is factorial with its entire set of traces. Right, so a finite von Neumann algebra is my next example of one of these. So this is a construction. This is something that Sam observed in his thesis. N T of n is T star when n is W star finite.
You say that George observed this while I was giving the talk.
Yeah, George observed this. It's turned out to be, it's somehow not an important example in terms of applying the theory. It's a very important technical example at some point. So this is, and then this one is always factorial, and that's right because T of n is a face in T of n. And then,
since you don't assume that M is a factor, T of M, it's non-normal traces also.
Yeah.
Then. Okay.
Yeah. So this is a weird but technically important example. This is going to be factorial if and only if X is already a face. So you can check that if it was a face here, it was a face upstairs. That's something to be checked. And then the one up there, I can't reach up there. The finite von Neumann algebra with a given trace is factorial if and only if it's already a factor. So at least that part, from that point of view, it's not a bad thing. Okay, so 2 more examples, and then I should move to the next part of the talk. So if I take K to be compact, say M, let's say 2-1 factor. This is an example due to Ozawa. You can consider C sigma from K to M, which is continuous functions bounded functions such that f is 2 trace m continuous, and this is a T-star algebra with the set of traces being given by all measures in k. So this with probability measures, and k is T-star. It's the trivial W star bundle with fibre m and base space k. A load of the non-commutative laws that we saw in earlier talks can be cast in languages like this. It's not clear. I mean, it's up to you whether that's a useful thing to do or not, but they fit into this. Let me now give you a very different looking example. So let X be a metrizable showcase index. If you've not heard the word showcase index before, so it's a technical condition, it's a simplex for which every point on the simplex is uniquely written as a boundary measure of the points on the boundary, whatever that means. Think of it though as an immediate, in Con's theorem we have the abstract condition of injectivity telling you that you have a finite dimensional inductive limit structure. This is an abstract condition on a simplex. All separable C-star algebras gives rise to trace spaces with metrizable showcase indices, but it's an abstract condition that guarantees an inductive limit structure. So metrizable showcase indices are precisely the inverse limits of finite dimensional simplices. So I can write x1, x2, dot, x is the lim in this direction of xn, with these guys being finite in simplices. Right, so this is, if you like, these abstract conditions to hyperfiniteness in the setting of simplices. So let's call that star, and I'm just specifying arbitrarily through this abstract structure these connecting maps and not telling you what they are. Of course, there's many ways of doing it. It's certainly far from unique. And then what I'll do is I'll form a map in the other direction. So I'll take copies of R indexed by the first, the extreme boundary of the first simplex, and I'll map them into copies of R indexed by the extreme boundary points of the second simplex, and so on and so forth. And this is not hard to do at all. You just use that R has got full fundamental group so that you can, put one direct summand of R into some proportion of another direct summand of R, and you'll realise precisely these maps. So I'm not planning to tell you how to perform constructions on Tracially complete C-star algebras. They'll be eventually in the paper, but you can sort of go through your favourite operator algebra constructions: direct sum, tensor product, inductive limit, ultra product, and they all work in the same way. You do it at the C-star level, so you do a purely C-star construction, you work out what the right set of traces are, you complete with those traces, and that gives you the tracially complete version of this construction. And of course that's what you do for the spatial product in von Neumann algebras. You do the C-star spatial product, you identify the trace, and then you do this completion process. A little bit of a silly way of doing it, but that's works for finite von Neumann algebras. So I will take, therefore, the inductive limit in the category of T-star algebras which exists, and you can check all that, and that gives me an example of a Tracially complete T-star algebra. This one is obviously AFD or hyperfinite, whichever you prefer, and it will be factorial, although I'm not going to check that. Okay, so that's another example of a Tracially complete T-star algebra. It is not obvious, I think, that that's independent of the choice of inductive limit process in star, but it's also not hard. You can use Murray von Neumann's original proof of the, essentially Murray von Neumann gives you uniqueness of maps from here to here up to approximate unitary equivalence by the affine function from here to here they induce, and in this way you can obtain you can show that Rx is independent of all the choices. So that is our canonical hyperfinite tracially complete C-star algebra associated to the space X.
Approximate unitary, it's not just unitarily conjugate?
No, I think maps from R to R are, you know, so if it was finite dimensional algebras into here, it would be a unitary conjugate. But maps from R to R are classified.
That's approximate. Yeah, but I thought you were making your choices using the fundamental group somehow. Well,
Yeah, well, no, if I chose to do it that way, but I'm now saying just do it however you like.
I see.
So independent, you know, all I care about is that this map realizes this map, and I know how to do it using fundamental group, but maybe there's a cleverer way of doing it.
Sure.
Still, I get the same construction. So that's the hyperfinite tracially complete C-star algebra on the space X. And we have proved along the way, and can prove along the way, the Murray von Neumann uniqueness theorem, that in fact any hyperfinite factorial tracially complete C-star algebra of base space X is indeed that one. We didn't actually prove that in the paper, so in fact in the paper we will prove a more general theorem and collect factors as a consequence. So that's the first part of the talk. So like that's what the definitions are. So what do we want? What's the big goal here? The goal is to obtain a full version of Con's theorem in the setting of tree. Con's theorem, stroke Elliott's theorem, the two big structure and classification theorems for von Neumann algebras and C-star algebras, and even von Neumann algebras and even C-star algebras, respectively, in this setting. But you might then want to ask, well, why do you want to do that? Why is that in itself a useful thing to do? Because really, I mean, all of the fact that there is a structure theorem and a classification of these T-star algebras is something that's becomes sort of evident through the way the classification program of C-star algebras has gone, and you can write the classification theorem for C-star algebras without ever referring to these tracially complete C-star algebras, although you will be using them in the background. You will definitely, this work really aims to pull out this part of the classification theorem for C-star algebras and make it much more visible. But why do we want to do that? And this comes back to the sort of thing that Corey was discussing in his talk, that post the classification theorem for amenable C-star algebras, you can imagine compelling and really powerful uniqueness theorems for C-star dynamics. We've seen the dynamical Kirchberg-Phillips theorem appeared on the archive earlier this year. We can imagine that there will be powerful uniqueness theorems in the stably finite setting for group actions. We can imagine a full version of Popper's classification theorem and uniqueness theorem for subfactors in the C-star setting using some sort of equivariant KK. And I really don't believe we'll be proving that in one go. So I do think that when we want to prove theorems like this in the stably finite setting, the process will be take the beautiful theorem that exists in the finite von Neumann algebra, get it fully realized in the tracially complete setting, and only then try to build the C-star version if you want more than one trace. Of course, if you're happy with just a unique trace, then this is just the von Neumann theory. So this is the process you'll need to follow, I believe, if you're trying to build versions of these theorems in the C-star setting with more than one trace. Okay, so that's well over half of my time and well under half of my material. So let's go to the second or last bit. Oh, no, before we do that, let me advertise the question I wanted to advertise. So now I am in a position to state the trace problem. So the trace problem question, which I'm calling the trace problem, if mx is factorial, T star is x, all traces on M. So on tracially complete C-star algebras, are there any non-normal traces or non-2x continuous traces? But only in the factorial setting. And notice, of course, that in this case, where there are sort of normal and non-normal traces, that this isn't factorial. So for a general finite problem. Okay, so let's get rid of some. So that is the trace problem, and I really encourage solutions to it. And a positive answer to this would deal with the fact that there are no weird traces on the tracial condition. I would like to believe this is true, but I honestly don't think there's any intuition for this. So. Okay, so what do we need to do structure and classification? Well, we certainly need some amenability. So let's stick to definition, stroke theorem. If mx is factorial and t star, you've got a choice. How would you like to define amenability? Would you like to define it by looking at fibres, or would you like to define it globally? And the theorem is that, of course, it doesn't matter, so TFAE is the theorem that pi tor of m double commutant is injective. I only need to check for all extreme traces, so let me check for all extreme traces. If it holds for extreme traces, it'll hold everywhere, if and only if m has the 2x completely positive approximation property. So you take the formulation of nuclearity in norm and you just 2x it everywhere, or you take the characterization of semi-discreteness and 2x it everywhere, which is if and only if all the traces on X are uniformly amenable traces in the sense of Finite ground. So our proof of this is quite scenic. You get to go on a sort of large tour of operator algebras, and in particular get another view of Con's theorem, right? So I would really like. I don't know whether this is a hard result or not. Maybe there's just a really cute harmonic trick that proves it, but we haven't found it. So in particular, one consequence of this theorem, in particular, it follows that if A double star thin is injective, let's suppose that that this is an embedding, so I've got sufficiently many extremal traces. This is the same as A having 2x CPA. Maybe I need 8 CPA. And this is if you said if A bidual is injective, the fact that then A would just have the completely positive approximation property. That's an easy application of Handbag. No Con's theorem needed. But if you don't assume that you have all of the bidual, Handbag is not applying, and I can't see how to prove this. We can't see how to prove this without going through Con's theorem. But if you drop the finite part here and ask for completely positive problem, the direction in this direction, which is the hard direction of our results, let's emphasize. I can't see how to do that via a Handbag trick, but maybe there is a Handbag trick. So I would like to advertise this.
The CP-AP is, if you just take X to be a single trace and M is it's just the semi-discrete.
Yes. Yeah. So this is precisely in the von Neumann situation, this is just injecting if and only if semi-discrete, which is of course part of Con's theorem, but maybe I should, to avoid using Con's theorem, maybe I just say semi-discrete here. And what I want to know is why is pointwise semi-discrete the same as uniform semi-discrete? In any event, that was the theorem. The definition is these are immutable. Therefore, they're going to be amenable whenever A is nuclear. Those ones are amenable. But there's still loads of work to be done. Nobody's yet set up like cross products in this situation and pinned down amenable cross products. Actions of amenable groups on these tracially complete algebras preserve amenability. It will be true and it will need doing, but it hasn't been done. Warning though. If you take L infinity R as a finite von Neumann algebra with all of its traces, this is not amenable. As a T-star algebra. Because, for example, if you take an ultra-limit trace, the GNS representation associated with that will be R omega, which is not injected. So finite von Neumann algebras with all their traces are too big. And it's just like you would not expect a finite von Neumann algebra to be amenable as a C-star algebra. A finite von Neumann algebra, all its traces is not going to be amenable as a tracially complete C-star algebra. My guess is a finite von Neumann algebra. I haven't checked this. My guess is a finite von Neumann algebra will be amenable as a tracially complete C-star algebra if and only if all of its fibers are amenable and there's finitely many extremal traces. But maybe I have to be careful about. Maybe I take a type 2-1 von Neumann algebra if I want to say that. Okay, so that's a very short section of amenability. There's much more to say here. At some point, I'd love to give some talks on the proof of this theorem, but that's not for today. So next is how did Con prove injectivity implies hyperfiniteness? Well, the first part of his proof was to show that injectivity implies property gamma. So I am in danger of running out of time, another 6 minutes, so let me there's a theorem, so recall that 2-1 factor has gamma by definition if and only if, for all finite subsets and for all epsilon greater than 0, there exists a trace-free unitary, trace U equals 0, U approximately commutes with the finite set. And then paper 1969 was a really great year for central sequences in von Neumann algebras. Deuce McDuff published 2 papers in the Annals on the subject, and then an important paper as well in the Proceedings of the London Mathematical Society, where she characterised McDuff factors. But also in that year, there's a somewhat more obscure paper by Dixmier in Inventiones, where he shows that this condition is equivalent to the following fact, that for all or there exists n greater than root 2, your choice, there exists projections P1 up to Pn in n omega intersection n commutant such that trace of Pi is 1 over n. So this was Dixmier's characterization of property gamma as sort of being like diagonal central sequence elements of all traces. And I think this one is not as well known as Deuce's work from the same time. And of course, in the theory of 2-1 factors, my understanding from the outside is that every time you want to use non-gamma, you use this one in a spectral without formation. Every time you want to use gamma, you morally use this one. So when Guy and Popper are proving, for example, that 2-1 factors of property gamma are singly generated, it's this characterization. So negation of property gamma, this one. And of course, this, if and only if, is quite easy to prove. It's a little bit of functional calculus. We don't have good functional calculus in T-star algebras, so we can't prove this characterization. We need to pick one of these definitions. We wish to use property gamma, so we did this one. That's the definition. N x has gamma if and only if this. So if and only if for all, or there exists, your choice, n greater than 2, there exists projections P1 to Pn in the Tracially complete ultra product. Remember I said that you can go performing your preferred constructions in the relative commutant, and that they need to be trace 1 over n all traces, and for technical reasons what you need is trace A pi is 1 over n trace pi for all allowed traces and the allowed
Trace A.
Trace A, thank you. For all allowed traces, and the allowed traces we write as x upper omega. I'll tell you what they are after the talk if you really want to know. And that should hold for all A. It's very annoying that we also, in Dixmay's characterization, you only need to divide the unit. For us, we need to divide everything. If x has compact extremal boundary, it's automatic that if P satisfies the condition without the A, then it satisfies the condition with the A. If the boundary is non-compact, that's not true, but we don't know of an example where if you divide the unit, there's not some other sequence that witnesses property gamma. So I don't know whether I need the A's here or not. Okay, so that's the definition of property gamma, and the second question is, that I wanted to emphasize is, do we need the A's, but I'll pass on that. What property gamma allows you to do is transfer local properties to global properties. There's a very precise statement here, which at least one now, probably now even two of my collaborators insist is best formulated in the language of continuous model theory. They haven't persuaded me of the merits of that as of yet. So there's a very precise statement of what I mean by transfer local to global. I'm going to give you just an example of what a local to global transfer theorem looks like by stating the classification theorem. So here is the theorem. So let's let mx be amenable factorial T star. Well then the following are equivalent. M is hyperfinite, defined to be inductive limit of finite dimensionals in the category of T star algebras. N is McDuff, in the category of T star algebras. I need to add 2x separable as well. N has gamma, and M was just Rx, and of course I mean Nx is Rx, the one I specified. And moreover, if delta E x is K is compact, this is also, so if this, that Nx is this C sigma KR. So this is an example. The hard implication is gamma to this, and that's the example of local to global. You knew that fiber-wise, it sounds looking
Something like no type.
Oh yeah, thank you. Yeah. No type 1. So I exclude any matrix bars. Yes, that's that. Yeah, so locally at each trace you knew that mx was the DNS representations are, but globally you don't. So the risk of slightly annoying, I would like to leave with just one question. The trace problem is a question I really care about, but this is a big question. So if mx is factorial T star 2x set and no type 1 fibers, I think that's my preferred terminology, must M have gamma. can you force through the first part of Con's theorem where he proves injective implies property gamma? So are all of these things hyperfinite? I need amenable, sorry, as well. So I want amenable to imply gamma. Amenable. So is gamma automatic from amenability? This lands in the category of Stefan's class of problems to which I have no idea as to the answer. But it will have big consequences. This would prove the Thomson-Winter conjecture, which has been around for a long time. I have a subsidiary version of this question, which I will allow people to ask me about in the coffee break, which I am sure the answer to is yes, but I equally can't prove it's another. So that's the division. So I have an easier version, which I'm sure is true. Also would have big implications for C-star algebras, but not quite as big. Thank you very much for your attention.